This video, I'm going to talk about the last topic regarding area between curves, which is the case where your curves are given in terms of the variable y instead of the variable x. Um, Let me start explaining. It's hard to talk about it without writing down what it actually is. So there are some regions that can't be described basically as the area between two graphs of functions, right? So I'm going to draw like an abstract example, but then I'm going to do a practical example so you see how it looks. But basically, for example, you could have a function or a curve that looks like this. Say, right? And a different curve that looks like this, for example. Yeah. And you might want to compute the area between these two curves from say that this is A and this is B. So chop it off right here. It didn't look so good. Let me erase that. Okay, so something like this. And we want to compute the area inside, right? So we want to compute this area between these two curves. The thing is that, as you can see, these curves are not given as a function of x, right? Functions of x can't, well, so here, for example, it fails the vertical line test, right? One value of x is associated to two different y values, or even three, depending on how you draw this vertical line here. So these are not functions of x, but you can actually write these curves as functions of y, x in terms of y. Okay, so say that, and basically everything is the same. You just have to kind of tilt your head to the side because now the x-axis will play the role of what the y-axis was playing before. So this green function, for example, let me call that, so let me make sure that it's equal to my notes here so I don't mess it up. So this should be x equals f of y. Okay, so the x coordinate is given by the value of the y coordinate. And let me call this one x equals g of y. Okay, and so this one is on top, right? So the green curve is on top of the blue curve because look at the direction of the x-axis, right? It goes to the right. So the more to the right you are, then you are bigger. Your x value is going to be bigger, right? So on the y-axis before, it was being on the top meant being bigger, and being in the bottom meant being smaller. But now being more to the right means being bigger, right? So the green is bigger, so more to the right, or what was on top before, and the blue has smaller x values, right? So in any case, we're going to have two curves given by x equals f of y and x equals g of y, and we are going to assume that for all y in the interval a b, the function f is bigger than the function y, then the area here that we want to compute, the area A, is equal to the integral from A to B again. But now, what we're going to do now is, instead of chopping up our area with these vertical rectangles, now we're going to chop it with horizontal rectangles, right? So you can draw tiny rectangles like this. The height is very tiny now. It's going to be a delta y because it's in the y variable, right? And the the base now is pretty big, and you can compute the length of this base by looking at f of y minus g of y, right? So you look at the bigger value, f of y is the bigger, minus g of y, and you can compute this length, right? And so adding up all these rectangles and sending delta y to 0, you get this integral formula. The area is going to be the integral from y equals a to b, f of y minus g of y dy. Okay, so the thing is that now you get an integral in the y variable if your functions are given in terms of y. Okay, but it's a very similar concept. It's just kind of tilting your head to the side and then integrating. So let's do an example to see how this works. In practice. All right, so let's find the area enclosed by the curves y equals x minus 1 and y squared equals to 2x plus 6. All right, so let's try to solve this problem. We start by drawing again, right? So most of these problems you need to draw, or all of these problems, computing areas, you need to draw to see what's going on. So drawing this line is pretty easy. So let's do that first. Although we're going to have to make sure to make space for this parabola. But okay, if you're careful, you can do it. Okay, so let's say that this is, so when x is equal to 0, y is equal to negative 1, right? So this is negative 1 right here. So let me draw this line in blue. Okay, so this line, the y-intercept is negative 1, and then it just has slope 1. So it's kind of like a diagonal like this. So that's that line, the graph of that line. And now for this thing, we have to kind of, so as you see, y is not given as a function of x because you have this square here. But you can write x in terms of y. So if you do that, let's see, I'll put 2x to the left, and then I'll do y squared minus 6. Okay, so I just took 6 to the other side and I flipped the equation. Right? Y squared minus 6 is equal to 2x. So x is equal to y squared over 2 minus 3. So this is giving x in terms of y, right? And if you think about what's going on here, so well, here's the x-axis and here's the y-axis. This is just a positive parabola. And when y is equal to 0, x is at negative 3, right? So, sorry. All right, when y is equal to 0, x is at negative 3, correct. So it's somewhere over here. Let me use the, so this should be negative 3. And then it just opens up just like a standard parabola. Okay, it kind of looks like this, right? So if you tilt your head, it looks just like a normal parabola, and this negative 3 kind of pulls it down in the x-axis, right? So that's what it looks. And we are trying to find this area in here, right? So we could try to figure out how to break this into an integral in x, right? But as you know, one thing that you would notice is that there's this interesting part here where to the right of this red line, blue is in the bottom and purple is on top. So you could use our normal formula. But then on this part, purple is on the top and on the bottom. I think I want to draw this again, actually. I'm not super happy with this drawing, so forgive me, but... Okay, this looks better. So this is y equals x minus 1, and this purple curve is y squared is equal to 2x plus 6. Right, so as I was saying, let me draw again. So in this part here, to the left, blue is in the bottom and purple is on top. But then to the right, purple is in the bottom and in the top, because in this part, purple is actually not a function. And you have, it would be not the greatest idea to try to compute this this area, using the x variable, okay, to chop up. So don't chop it up with vertical rectangles, chop it up with horizontal rectangles, which means that we're going to use this formula, right, that I gave here. So first we need to figure out what is the range. So the area that we want to compute is this area, right, between these two curves. But to compute the integral, we need to figure out what is the range of the y variable in this region, right? So we need to figure out what is this point, that's A, and then what is this point here, right? That's B, right? And how can we figure it out? Well, these points are the points where the two lines intersect, right? So they have to satisfy both of the equations at the same time. And so we can try to just do that to solve for them. So whatever coordinates these points have, they have to satisfy both that the y coordinate is equal to x minus 1. They also have to satisfy this equation, that y squared is equal to 2x plus 6. Right, both of these together. And if we solve these equations together, we'll be able to figure out what a and b are. Those will be the y coordinates. Right, so basically, I'll just take this y equals x minus 1 here. And this tells me that x is equal to y plus 1. Right? And then if I take that and I plug into the second equation, I'll get an equation just in terms of y, a quadratic equation in y, which I can solve, right? So y squared is equal to 2 times x, which is 2 times y plus 1, plus 6, yeah? And so y squared is equal to 2y plus 2 plus 6 plus 8. Let me put everything on one side. Y squared minus 2y minus 8 is equal to 0. Let me do a little thinking here. So the roots have to multiply to 8, to negative 8. And they have to add to 2. So 4 and minus 2, right? Negative 2 or 4. Right? If you multiply, you get negative 8. If you add, you get 2, which is this with the negative sign. Right? So a nice quadratic. So these are the two solutions for y, right? So again, what are we doing? We need to find this a and the b. These are the y coordinates. These are the y coordinates of these points, which are the intersection of these two curves, right? So these points, the red points, so say for example this point here on the top, it's on the blue line, so it has to satisfy this equation, y equals x minus 1, but it's also on the purple parabola, and so it also has to satisfy y squared is equal to 2x plus 6, right? So we take this system of equations, these two equations together, and we try to figure out what are the solutions. So I just use the top equation to write x in terms of y, because then I would get an equation just in terms of y from this quadratic here, right? Which is what we got, and we solved. Y is minus 2 or 4, so clearly a here is this negative value, right? Is negative 2. And b is 4. Okay, and the top function is the function that's more to the right, right? Is the blue function, the line, right? So, and the purple function is the smaller x values, right? So if you want to compute this area, okay, so let's write down the area. It's going to be the integral from negative 2 to 4, and then you need the height of, the width of this horizontal rectangle So you take the value here in blue. So the x value. Oh, so you need to write x in terms of y, which is right here, right? So it's y equals x minus 1. You can also say that it's x equals y plus 1, right? So if you know what the y value is, let me not use blue. For a given value y, uh, this x value here is y plus 1, right? Because it's on the blue line, minus the x value on the purple, which is given in this way in terms of y, right? So it's going to be y plus 1 minus um, y squared over 2 minus 3. Okay, dy. All right, so this is this formula here, f of y minus g of y. Right? This is f of y, this is g of y. The blue function was on the top, right? It was more to the right, right? So, and then you just need to take the value here uh, of the x value over here minus the x value over here. You're gonna get this length, which is the width of the base of this rectangle, right? So this is the base of the rectangle, and this is the height, which is just dy. Right, so that value was y plus 1 because we wrote this equation as x as a function of y, so it was y plus 1. And then this, to get the value for the purple, you just use here x in terms of y. This is the function, y squared over 2 minus 3. Hopefully that made sense. There's a little bit of a gymnastics to understand what's going on because everything is flipped, right? But if you have questions, please just come to office hours and I'm happy to explain this again. But now this is not a hard integral to solve, right? So let's maybe distribute these things a little bit. We're going to get negative y squared over 2. And then we have plus y. And then a plus 1 plus 3, which is a plus 4 dy. We take an antiderivative. This is a minus. This y squared will turn into a y cubed. And you're going to divide by 3, so you're going to be over 6 now. The y will turn into plus y squared over 2, right, with the power rule. And this constant 4 will turn into 4y. Okay. And plug in y equals 4 and y equals minus 2. I haven't really solved this, so hopefully the math is not going to be too hard. Okay, so this is going to be, I'll do it slow, minus 4 cubed over 6 plus 4 squared over 2 plus 4 times 4 here minus, now you plug in negative 2, negative 2 cubed over 6 plus negative 2 squared over 2 plus 4 times negative 2. Okay, let's see what we can simplify here. 4 cubed, so 4 squared is 16. If you multiply that by 4, you get 64, right? I'm right? So 4 squared is 16 times 4 is 64. So this is minus 64 over 6. This is plus 16 over 2. This is plus 16. So this negative 2 cubed will turn into a negative 8. With this negative sign, it will turn into a plus 8, right? So this is a negative 8 plus 8. With this negative sign is a negative 8. Annoying, I know. But this is a 4 over 2 with a negative sign turns into a minus 4 over 2. And this is a negative 8 with that negative sign turns into a plus 8. Now I just have to add these fractions here. these are both over 6, so let me put them together. So it's negative 64 minus 8 will be a negative 72 over 6. This is an 8, and that's an 8. So this plus this is a 16. With this, that's a 32. 16, 8, and 8 is 32. And here, minus 2, it would be a plus 30. All right, so let me make sure that I didn't mess up here. Negative 64 minus 8 is negative 72. 16 with 16 is 32. And then minus 2 is 30. Okay. 72, the 6 divide, so that turns into minus 36 over 3 plus 30. And 36 over 3 is just minus 12 plus 30, which is 18, right? That's the area. So the area. All right, not so bad. So hopefully it made sense. What happens in this case is just as you saw, um, the example just asks you to find the area between two curves, but then you see that there's an I squared here. It's not going to be a function. Y is not going to be a function of X, right? And in fact, when you draw the picture here, you see that there are parts, this purple curve is just not a function of X, right? But that's okay. You can write it as a function of Y, and then you can slice this area with horizontal triangles. And it's actually quite similar to what we've been doing. Just a little bit of uncomfortable thinking because everything is flipped. All right, so this concludes the area between curves. Yeah, so we got this integral here and computation there. So this concludes the section area between curves. And in the next video, we're going to start talking about volumes. All right, see you then.